So now I let Homanga talk. I will first say that Homanga is from the University of Toronto, and he worked on learning, reinforcement learning policies um, for like it's trying to apply this into robotics context. So I let Omanga start and present his work. Yeah.
Thank you. I'll just share my screen. We can see my screen, right? Uh, yes, so I'm going to be talking about policy transfer in robot learning, and particularly using reinforcement learning. So this is the paper I'll be covering, which was presented in ICRA this year. So to start off, what is robot learning? This is kind of a research field at the intersection of machine learning and robotics, where we aim to develop learning algorithms for controlling robots to do particular tasks. So the idea is that we should be able to use data to learn automatically without having to specify the controllers themselves. Uh, so why is robot learning useful? Because learning from data allows us to generalize to different environments and tasks. So it avoids the issue of manually designing controllers for different tasks, which is both challenging as well as time consuming. There are multiple shades of robot learning algorithms, and two popular paradigms are reinforcement learning, when agent interacts with the environment through trial and error learning, and imitation learning, where there is some sort of expert demonstration which the agent needs to imitate in order to learn. So the talk today is actually going to be agnostic to the type of policy learning algorithm that is used. Yes, and so we come to the question of why do we need transferable policies? And the idea is that we should be able to adapt to different environments quickly without having to train from scratch in every environment, so that we have very less on policy fine tuning in the new environment. And this is important to have high sample efficiency, that is to minimize the number of interactions the agent has with the environment. This is important for safety critical situations where we do not want to execute a suboptimal policy in a potentially risky new environment. So we want that the policies that are trained in existing environments are transferable to the new environments. So the motivation for our particular work was that most current policy transfer approaches do not efficiently adapt to different dynamics, variations at test time. So the dynamics could be the dynamics of the agent, like the mass, moment of inertia, friction coefficient between the joints, or it could be dynamics of the environment, like friction between the agent and the surface of the environment, or the coefficient or the gravitational acceleration, the slope, terrain, etc. So we want to learn policies that transfer to these different dynamics variations for any given test environment. So coming to the insight of our approach, so the key insight is that we should explicitly condition the policies that we are learning on the dynamics of the environment uh, during training. So during training, when we know what the environment is, we know what the dynamics parameters of the environment are. So we should train policies that explicitly condition on those variations. Because the dynamics parameters, so in the figure, we don't know the mass or the friction of the block, so the agent doesn't know it in a traditional learning paradigm. So, but if we explicitly condition the policies on those dynamics parameters, then we can learn policies that kind of adapt to a test environment given the dynamics parameters of the test environment. And then the next challenge becomes we don't know the dynamics parameters of the test environment. So we should be able to have a scheme that learns the dynamics parameters of an environment given some state transition rollouts in that environment. So the agent interacts with the environment and it collects state, action, next state tuples. And using those tuples, we should be able to estimate what the dynamics parameters are. And that is kind of the second insight. The third insight is that in order to be applicable to some safety critical systems, we should not have to use on policy rollouts in the test environment. By on policy rollouts, I mean transitions that are collected using the policy that we are training. So we should be able to leverage some sort of off policy data, data that has been collected by some other policy, which could be a prior safe policy, say a PID controller or anything else that we have. And using that data, we should be able to perform the transfer to the new environment efficiently. And like I said, we don't want on policy fine tuning in the new environment. So summing up, what we essentially want is to capture the essence of tasks like knowing how to ride a bicycle and condition this on the dynamics variations like change in terrain, weight of the bike, gravity, etc. So when we learn to ride a bike, we are able to generalize to different terrains. And so we want to train policies that can achieve the same sort of generalization and adaptivity. The final point is that we also want to make the model adaptable to variations in motor noise, which is one of the main reasons for domain mismatch between the simulator and the real environment. So by motor noise, I mean some sort of noise that is added to the action that the agent is supposed to take. Now we kind of formalize the main ideas. So we exploit the fact that we know the true dynamics in the simulator, and through that, we train a dynamics condition policy. And we also learn to estimate the dynamics parameters of the environment, borrowing some of the ideas of meta training. And through this, we train a dynamics estimator that takes in state transition data and outputs the dynamics parameters of the environment. And the two modules, the dynamics condition policy and the dynamics estimator, are trained separately. So they're decoupled, which is important uh, because we can then train the two separately. So the dynamics condition policy has a few components, and this is sort of standard, I guess, in learning uh, policies of this form. So here we have an observation that we get from the environment, which is OT, and we encode that through an observation encoder, F5, and we also have some dynamics parameter of the environment, which we are calling eta E on the right, and we encode that separately through a separate dynamics encoder. And the two encodings are concatenated to a latent state. So we want to encode the two separately because if you see the observation has a uh, subscript t, so because it varies at every time step, whereas the dynamics parameter of the environment is fixed during a particular episode, so it doesn't change with every time step because the environment remains the same. So since the two inputs have different frequency, so we want to encode them separately in order to have better latent representations. And then we concatenate them in this z vector. And then we finally have an action decoder that takes as input this latent z and outputs the action. And all of these are kind of trained end to end. So we don't train the latency separately because we don't want the Z to capture anything particular. So we can't have sort of supervision for training Z. So we train the entire thing end to end. And the idea is that after you have an action, if you're doing reinforcement learning, then we apply that action in the environment, get some reward signal, and use that to update the entire pipeline. Or if you're doing imitation learning, then we have expert actions and we compare our action to the expert action and use that difference to update the entire pipeline. So this is a fairly generic. And so the eta E is known during training because when you're training it in a simulator or even in a real environment, we kind of know what the dynamics parameters of the environment and the agent are. So we use the fact that we know that, and so we train it in this way. And as you can see here, we have two auxiliary tasks, state reconstruction and action reconstruction, which are used to regularize the latent state. So these are again not our contribution, but they're used fairly commonly to learn a bit better latent representation. So the state reconstruction task basically tries to reconstruct the observation given the latent state. So we want to learn latent states such that they capture all the information that is necessary to be able to reconstruct back the observation. And we also have an action reconstruction task, which is also called this inverse action model, where what we do is we take a particular latent state and the next latent state, and we try to infer what action caused the transition from this particular latent state to the next latent state. So we take zt plus 1 and zt, successive latent states, as input, and we have this inverse dynamics model G inverse, which tries to predict what action the agent took. And we can train this because you already know what action the agent took, AT. So yeah, so we have these two auxiliary tasks. And the way we train the dynamics condition policy is by randomizing this eta E. So we randomize the parameters of the simulator, which shows different mass of the agent, different moment of inertia, different friction coefficient. We vary them within a range. And at the start of every episode, we choose a particular setting of this dynamics parameter, so particular eta E, and we train it using that for that particular episode. And at the beginning of the next episode, we change that, and so on. So this is called dynamics randomization, which is again a common technique for sim to real transfer. But in this paper, we are using it to learn dynamics condition policies. And we come to the second component, which is the dynamics estimator. So here we have some rollouts. So state, action, next state. We have these rollouts, and we use these rollouts to estimate the eta of the environment. And we can again train this because when the agent interacts with the environment, we collect these rollouts. And we also know what the eta is during training because we are varying it ourselves, so we know that. And the way we do that is through some sort of so the idea is that if you're given just one rollout, one tuple, like observation, action, next observation, so you can't possibly expect the agent to learn what the friction is of the environment because you need some sort of temporal sequences in order to see how the states evolve, and using that you can better estimate what the dynamics parameters are, like friction. So we have, instead of having just one tuple, we have a sequence of tuples. So the sequence starts from n is equal to 1 to k times capital T, and we have k separate elemental dynamics estimator. So we fit, so these are normal distributions. So we fit k different normal distributions to different parts of the sequence. So because you don't know which part of the sequence will be the best for inferring the dynamics parameter of the environment. So since we don't know any better, we chunk the sequence at k different steps, try to estimate the dynamics parameters at every chunk, and then we combine the knowledge that we have from all the different chunks through this aggregator. So this aggregator is an expectation of all these different Gaussians, and we also have a noise to account for the noise in the simulator, and we take the expectation of that, and that is basically the aggregator. And then we estimate the dynamics parameter of the environment eta hat E, and we already know the true dynamics eta E, so you're able to train this model. Then, so that was during training. So during test time, when we are given a new environment, we don't know the dynamics parameters of that environment. So what we do is we assume we have some sort of policy rollouts in that environment, which in this paper we took a random policy to collect that. But for safety critical systems, we might assume some sort of controller that we have, like a PID controller that is safe, and we can use that to collect these transitions. So since you already trained the dynamics estimator to estimate the dynamics parameters uh, uh, given rollouts in the environment, we can use that trained model for the test environment in order to estimate the eta hat of the test environment, and we use that eta hat for the dynamics condition policy. So we condition this policy on this eta hat that we're estimating through the dynamics estimator, and then we have the observations at every time step, and you can output the action at every time step since this has already been trained. So also we can do some sort of further fine tuning of the dynamics condition policy in the test environment if it is necessary, but the key idea is that we already have a very good policy in the test environment zero shot without having any fine tuning, and that is important if you're deploying this for safety critical systems. So coming to the experiments, we evaluated this on three continuous control tasks from this OpenAI Gym suite. And what you observe is that a model learns policies that are stable in a test environment and also achieves high rewards compared to baselines. Uh, yeah, so a few qualitative results which are not particularly informative, I guess. So on the left is domain randomization, which I'll talk about shortly, which is one of the baselines. Yes, so as I mentioned, we have a few baselines. So one of them is domain randomization. What this does is that it has policies that are not conditioned on the dynamics. So just normal policies that take in observations and output actions. And it is trained by randomizing all the parameters of the environment, similar to what we do. And the idea is that if the variations in the training suite, in the training set of environments are sufficient, so if the randomization is enough, then the policy would have some sort of implicit understanding of the dynamics of the how the action should be taken depending on dynamics changes. So it is assumed that the policy would learn that implicitly, and what you get is when you train a policy across these different dynamics parameters, you get a policy that is robust to dynamics changes when applied to a test environment that is different from the any of the training environments. But our idea was to have policies that are adaptable to the test environment instead of being robust like domain randomization. And in domain randomization, one of the recent papers used an LSTM model, long short-term memory, which is a recurrent neural network that takes in not just the current observation, but the previous observations as well and predicts the action. And this performs slightly better than having a feed-forward neural network that just takes in the current observation and the action. And this is because the LSTM model can have a better implicit understanding of the dynamics changes simply because it takes in multiple observations. So this relates to our idea of having multiple observation tuples for estimating the dynamics because it is easier to estimate it that way instead of having a purely reactive estimator that takes in just the current tuple. And then we have the other baseline, which is model agnostic meta learning, which is a meta learning baseline that again trains policies such that you learn a good initialization. And when you apply it to a test environment, you can improve upon your learned initialization by some fine tuning in the test environment. So that is model agnostic meta learning. And we have this oracle, which we are comparing. So the oracle is the model, is our model that we are directly training in the test environment. So the oracle knows what the dynamics parameters are of the test environment, and that is directly input to the dynamics condition policy, and it trains in the test environment using the ground truth dynamics. So the oracle knows more than our method and the baseline. So oracle has the highest performance in all the three tasks, and this is sort of the best that we can do. So we're trying to see how close we are to that. And for manga, we have three variations. One is manga, the entire model, and the other three are models where we remove where we either don't have any regularization. So this is the regularization of the latent space, the state reconstruction, the action reconstruction. So we don't have that. That is no reg, and only S is having only state reconstruction, and only I is having only action reconstruction. And we observed that when we have the regularizations, we perform slightly better in the test environment compared to not having the regularizations. And we observed that we kind of reach close to the oracle in all the environments. Uh, so the previous result was for the test environment, like what performance we get. And now we see what happens when we let the policies initialize in the test environment and continue training in the test environment. So at time step 0, what we observe is after you have trained these three baselines, so DR is the domain randomization baseline, and this green is Oracle, is the Oracle baseline. So what we observe is that Manga has a very good zero-shot reward in the test environment, and that is because we have this sort of decoupled mechanism where we're inferring the dynamics separately and feeding that to the policy, and we've already trained the policy in different training environments. And so given a test environment, we have high initial reward, which is important, and then it quickly converges to whatever optimal reward you can get. And all the three methods kind of converge to similar rewards eventually, but Manga has this very good initialization in all the three environments. That is what this plot is showing. And so I didn't talk about motor noise variation. So modeling motor noise is tricky because we don't exactly know the source of this noise. So what we do is we assume a simplistic model where we say that motor noise is some noise, some sample from a distribution, epsilon t, which gets added to the action that the agent predicts. So it distorts the action by some epsilon, and we need to assume some parametric form of epsilon in order to be robust to motor noise. So what we do is we have this omega e, which is some sort of environment dependent parameter. So e is the environment. So this omega varies with the environment, and we have phi tau, which is a random network. So it is a neural network with weights that are random, and we have observation OT. So the idea is that we have motor noise that depends on an environment dependent parameter omega, and some function of a random network that depends on the current observation. So the motor noise epsilon t varies at every time step through this random network that depends on the current observation, and it depends on something that is constant for the environment. So it depends on these two different things. So we can either assume that a random network is known even for the test environment, or we can assume that it is unknown. And when we don't know this omega e, which is what we assume, we can estimate this the same way as we estimate the dynamics parameter. So we treat this as yet another dynamics parameter of the environment, and we estimate this along with all the other dynamics parameters like mass, moment of inertia, friction, and so on. And so we are able to estimate this, and we can assume that this tau is a known random network. And then what we are showing here is the magnitude multiplier of the noise. So we multiply this with some number k, so that k is denoting how big the epsilon is. So if k is large, that means the absolute value of epsilon is large because you're multiplying it. And what you observe is that when you increase the magnitude of the noise, the performance drops for all the environments. But when we have this manga noise version where we are learning this omega e along with the other dynamics parameters, then we perform slightly better compared to when you're not learning it. And that again kind of shows that how learning the dynamics parameters is essential in adapting to motor noise. So yeah, so I guess that concludes the presentation. But I'd be happy to take questions. I hope I finished on time.
Okay, if you have any question, feel free to unmute yourself. Thanks, really. Thank you, Manga, for the presentation. It was really clear and nice to listen to you.
Thank you. Should I stop sharing or should I keep sharing? We'll just stop sharing.
Okay, Ang is
Yes, so maybe it's already covered in the first part of the presentation. I didn't hear, but could you elaborate a little bit what's the dynamics parameters you were trying
Oh,
to?
yes. Yeah. So in the paper, we considered the mass of the agent, the moment of inertia of the agent, the friction coefficient between the agent and the environment, and the friction, the damping between the joints of the agent and the gravity of the environment. So these are the parameters that we covered. Yeah. And the friction between the joints of the agent kind of vary depending on the agent. So for humanoid, it has a large number of joints compared to Hopper, which has only two joints. Yeah.
Okay, and another question is that have you tried a little bit about the policies that accounting the history of the data, but without the explicit structure, like kind of you have the module considering reconstructing these dynamical parameters?
Yes. So
Let's say you have a policy with RN or something like that.
yeah, we considered that. Okay. I think let me just share back my screen. Uh, so here, uh, the domain randomization LSTM version is a LSTM policy that takes in previous states and not just the current states, a sequence of states and outputs the action. And we train it using the same domain randomization scheme that we use. So I think this is what you're referring to, right? So policy that takes in a sequence of states and outputs an action.
Okay, but for that one, you don't access to the real dynamic parameters, right? You don't have the label. You just have the data.
Yeah, we don't have the label. Yeah.
Okay, okay.
Yeah.
So that's and also, I mean, could you give a bit of comment on how this will compare with like the paradigm like math learning, like MAML, say that's
Oh yeah, so we have this mammal baseline. So the problem with metal,
sorry.
yeah, yeah. So the problem with this meta learning algorithms, especially like mammal, is that you learn a good initialization. So you train such that you learn a good initialization, and the idea is that you will fine tune in the test environment using that initialization of the policy. So you'll update the policy, and mammal requires very few rollouts in the test environment because it learns a very good initialization during training. But what we are trying to get at is we don't need any fine tuning in the test environment. So can we learn such that the policy directly adapts to the test environment without having to update it? And that was kind of this result that showed in the 0th episode in the test environment, we get very high reward because it directly adapts to the test environment. And that is what is missing from the meta learning baselines like mammal, which are based on learning initializations and then fine tune.
Yeah. And is there any plan to apply this to sim to real? Like,
yeah, so I did this during my internship at Preferred Networks, so in this company in Tokyo, And yeah, we didn't get a chance to try it out on real robots. But the problem with sim to real would be that uh, uh, yeah, so I mean, theoretically there is no problem, but theoretically what we can do is we train it on different variations of simulator. So we can change the parameters in the simulator, but we need to find a simulator that is close to the real robot, the first thing. And then we need to account for some sort of visual domain mismatch as well. Because the simulator, because for the real robot, we would not have the states of the robot in most cases. So we'd have to learn from images or LiDAR or some sort of data like that. And then we'd have to account for that visual mismatch as well. So I guess it is slightly challenging in practice, but theoretically, this is definitely applicable for Centurion. Yeah.
Okay, thanks.
Okay, we have another question. If the person who asked wants to unmute him or herself, it's welcome. Otherwise, I can ask. His work.
I think it was mostly answered actually by the. It was sort of asked again by the previous questioner.
Okay, perfect. Do you have any more questions?
Does this work assume that the observations are? I guess what are the observations in this work? Is it state extracted? You know, sort of directly from the simulator, or what?
Yeah. So here we just assume the states to be the simulator states, so not images. So the simulator state consists of I don't know, the joint positions and velocities of the agent, uh, the and some parameters of the environment. So basically, the state extracted from the simulator directly. Yeah, we plan to use image observations, but that was proving a bit tricky because we need to change the policy structure as well, like have some sort of convolutional neural networks and then process the images. And then also it becomes sort of like a POMDP if the images are not, images don't convey the full picture. So it becomes partially observed. So we just use the simulator states. But I think for transferring it to a real sim to real setup, it would make more sense to have images observations because it is typically difficult to get the states for a real robot system, especially the environment states.
Thank you.
Do you have any other question? Okay, see, yes, here we have another question. Okay, if the person doesn't want to ask, I will ask. There is no problem.
Can you hear me?
Yes.
Yeah.
Perfect.
Yeah, I was just wondering if, I mean, if you transfer it to a real world task, how would you compare if the dynamics parameters are matching? I mean, in this case, it's easier because you have a simulated world with known dynamics, right?
Yeah. Yes. Exactly.
I was wondering how you would do it if you had to transfer this to a real world task.
Yeah. So so like some of the baselines that we have here, like the especially the domain randomization baselines, which do dynamics randomization like we did, they actually show results for sim to real, where if you where the main idea is that if you train it on sufficiently diverse simulators, then you have essentially covered a large spectrum of what changes can possibly be, and then the real world is just one instance of that, which is a very strong assumption. But empirically, what domain randomization papers have showed is that uh, you are able to train policies that can adapt from sim to real, where the simulator and the real environment should be close, sufficiently close. So the simulator should be a good like simulator of the real environment that is necessary. But assuming you have something like that, then when you train it on sufficiently diverse simulation parameters, you're able to transfer the real environment. And so if assuming that is true, then this method will also transfer in the same way, because we are adopting the same dynamics randomization during training. Yeah, but there are like these two assumptions, that the simulator should be close to the real environment, and we are able to cover a sufficient breadth of dynamics parameters during training.
Okay, thanks. Just a follow-up question.
Yeah,
Uh, so I'm not familiar with the work about domain randomization, but
yeah.
I assume they consider the dynamic parameters are constant throughout the task, right?
No, they change it. They change the dynamics parameters at the start of every episode, like we do, but they don't have a dynamics condition policy. So the policy is not conditioned on the dynamics parameters that are there in the episode, and there is no dynamics estimation. So there is no method of estimating the dynamics parameters given data like we're doing. So you're just training a policy on different dynamics parameters and learning a good policy that is kind of an average of all the different conditions that you see. Does it
Uh,
make sense?
yes. No, I mean, what I meant is even in that case, for
Yeah,
example, if you're considering friction, uh,
yeah.
it's a very it's not a constant in the real world, right? Because depending on the
Oh,
direction you move, it can still change.
oh,
Uh,
I see.
so uh,
Oh, I see. That's a good question. Yeah, yeah.
it's
So
just
here, what
some,
you're assuming, yeah, is that for the test environment, the dynamics parameters remain same. Yeah, like while the agent is moving, like across an
the
episode
reason I
as well.
ask is it's something that I'm trying to figure out as well. So I was
Oh,
just seeing if there are ways to deal with dynamically changing dynamic parameters, if that makes sense.
yeah, there are actually. Yeah, so I can refer you to this paper. Uh, uh, can you see the screen?
Yeah, I can.
Yeah, so there here in this paper we did continual learning,
Mm-hmm.
where the idea is that the dynamics changes during the episode. So uh, yeah, so I think that is the setting you are referring to, and here by dynamics changes we meant so in this task, so pushing a block of non-uniform mass. So the block has different mass on both sides. So essentially there's different friction on both sides of the block, and in the other task we had this different. So during learning, the door kind of changes, like the handle of the door changes, and it must learn to grasp while this is continually changing the dynamics of the environment, and in this case the doorknob. So
Okay.
I think you should look at continual learning works,
Yeah,
maybe even this
it's
paper. Yeah,
similar to what I'm trying to do as well. Trying to formulate an online learning framework for
yes,
this.
yeah, exactly.
But thanks for referring to the paper. I'll definitely take a look. Thank you.
Okay, yeah.
Any more question? Okay, if you don't have any more question, I will just follow up on the discussion about domain randomization, because I found that it was kind of similar, like what you were doing to what they were doing. So I found difficult to understand what was the real added value, because you said that in domain randomization, they aim to develop robust policies,
Yeah,
right?
yeah,
But in your case, you're trying to adapt
yeah,
to a given new test environment, right?
yeah, yeah, yeah,
So my my question there is that not this capability of adapting a form of robustness too, like a form of robustness of the policies too?
Uh, uh, I guess, yeah, maybe. I mean, like the definition of robustness, I guess you can use it to mean adaptive things as well. But what I was really getting at is that, so in domain randomization, the policy is just the usual policy that takes in observations and outputs the action, and you don't have this explicit conditioning. So, and you train this across different eta. So this eta dynamics parameter is not visible to the policy, is not like explicitly given to the policy. So the policy must learn to have some sort of internal generalization of what action it should output depending on the observation and depending on this. But what we are doing is we are explicitly giving it. So so it's kind of easier, I guess, for the policy to generalize when this changes compared to when you don't give it. But then this introduces the additional challenge of how do you estimate this, and that is why we have this dynamics estimator, which domain randomization does not need to have, because it only has this part of the architecture in the policy. But like the intuition is that it kind of learns something that is good enough for a lot of different eta e, because if you learn, so there are different dynamics parameter of the environment, and you're learning something at the center of it, then it would be good enough for a lot of the environments, and that would have high performance under this domain randomization metric. But what we are doing is we also have this eta e parameter. So we have this good initialization, as well as when you feed in the eta e, then it moves closer to the particular environment, depending on the fact that we're able to estimate this reliably. So I think that is kind of the difference I was trying to get at. Yeah, but I agree that I guess robustness is also a form of adaptivity.
Yeah, I mean, depends a lot by the way you define it. And I was wondering, because you actually state that in the paper.
Yeah,
So I
yeah.
was like, maybe I should ask. And
Yeah.
another question, if do you have any other question? Mm, Like if I will first ask if someone else has other question, otherwise I will make another one. May I ask? Okay. This is a more general question, and it's about the limitations. Like I didn't find in the paper itself like a section that actually shows the limitation. You clarify a bit within the presentation,
Yeah.
but and this is a follow up with the Ang question. Um, like what from the limitation that you identified, how are you proceeding, and what are you doing?
Yeah, so I guess one of the main limitations is the limitation that we inherit from dynamics randomization, where we need to be able to train it on diverse dynamics parameters during training. So the range of parameters that we choose, like the value of, say, friction, the range should be large, and the test environment should ideally fit in that range. So if the test environment is out of distribution for whatever we are considering for training, then it would not be able to estimate the dynamics parameter of the test environment. And hence it would not be able to learn a good policy in the test environment. So that is the biggest drawback, that it can't generalize to out of distribution test environments, out of distribution compared to the ranges that are used in training. And that is also a drawback of the dynamics randomization itself. It can't generalize well. Uh, yeah, I guess that those are the limitations. But from a more practical point of view, this method cannot handle image observation. So that is definitely a drawback. But when we have images, instead of simulator states, even then we can do our randomization. So we randomize the pixels of the image, like we have different colors, different shades for the observation that we get. Like we vary the image in pixel space, and one of the domain randomization papers showed that you can generalize using that. So even when you don't have the actual simulated states to randomize over, you can randomize over the image space essentially. But even in that case, we need to assume that we have access to this eta e during training, which is probably a reasonable assumption if the training is in simulation. But if we are applying this method directly in a real environment, like we're doing real to real transfer instead of sim to real transfer, then we can't use this method because this eta e for the real environment is usually difficult to estimate. Like the friction between the robot and the agent and the surface on the slope of the surface. So those are difficult to get in the real environment. So that would be the second main drawback, I think. Yeah.
Okay, thanks. Thanks a lot. I think clarifies. So I will thank you again for presenting today. It was really cool.
Yeah,
And
thank you.
I will give you to clue about the next speaker. If there are no more questions, I mean, I will wait 1 more minute if you have other questions. Otherwise, I will move and give you the clue for the next speaker. Okay, I think we can continue. So let me share my screen again. Oh. Okay. So again, thanks Homanga for the presentation, and really it was nice to have you
Nice
as a
presentation.
presenter. And our next session will have a person. Okay, our next speaker got his paper awarded, and he's a volunteer at TEDx in Stockholm. I don't know if you already guessed who it's a bit hard, but our next speaker will be Taras, and he will speak about gesticulating agents, why and how, and we will talk about this awarded paper. So we will be happy if you want to join us. And
Yeah, sure. Yeah.
for all of you, like just a reminder, we have a Slack channel. So if you have any other question about the work of Manga, feel free to send us your email so that we can add you to the discussion and we can continue to talk about the work of Manga.